Hi guys, and welcome back to our second part of modeling in RFEM. As previously announced in the first tutorial, we are going to create this cantilever beam, this time using the dialog options in RFEM for modeling. To begin with, we can access all dialogs in the project navigator on the left side of the screen by right-clicking on the respective tabs or folders. Or we can access these dialogs using the insert menu up here as well. For instance, if we choose model data and select materials, you can see the option dialog box here. Within this tutorial, I am going to use mostly the project navigator for opening up these dialog boxes. And again, we will start with the nodes of our beam element. For that, we go up here on the nodes folder, and with the right click, we choose the option new node. Then this new dialog appears, and just like in the first tutorial where we did use the tables for creating the nodes, we are going to enter the coordinates of our nodes depending on a reference node. This will be the origin, and we are going to place the first node here, so the coordinates of this node will be 0 and 0. Then we click OK, and we do exactly the same for the second node. Right click on the Nodes tab and choose New Node. The coordinates for the second node, we enter here 3, which defines the endpoint or the length of the beam. Again, we hit OK, and then we can see that the nodes are set in the graphical area. So now to connect these nodes with the line in between, same procedure once again. With the right click on the Lines tab, in the project navigator, we open the dialog box for a new polyline. At the top up here, we can define the number of the line. Since we just have one line, this will be the first one. In the section below, we select the nodes to be connected, and we can either type in here 1, 2 for our 2 nodes, or like if you have a more complex model and you don't know the numbers of the nodes, there is also the option to select the nodes graphically. If we click here on the cursor button and select the nodes out of the graphical area. Next, we will continue with defining a material. Let's say again, just as an example, we enter here material 1 like in the first tutorial. Then we will enter our characteristic values from that example. Again, you will notice that after entering the modulus of elasticity and a Poisson's ratio, the shear modulus is automatically determined. We can close this by clicking OK. Now we are going to set the supports, and once again we can find in the project navigator nodal supports, and with right click we will open the dialog for that. So a cantilever beam is one of the basic types of beam elements, and remember this type is characterized to be a statically determinate system. For that we need 3 support forces or reactions as a minimum. Since this beam is supported at only one end, we have only one actual support here, which is going to be our first node, and at that support it has to have all of those reactions. For that, the support conditions here will restrain the beam horizontally and vertically. In case if we don't have anything else, it'll be allowed to rotate, and we don't want that, so we lock the rotation around the y-axis here. The graphic at the upper right corner gives you a nice visual illustration for that. Then we can click OK, and next we need a cross section for our beam element. In this dialog, we can either open up the library if we hit this symbol here, or we can just type in the cross section as well. Let's say we enter here rectangle, which will have a width of 100 and a height of 200, same as the one in our first tutorial. We can see below the cross-section properties, and down here we can choose the material for this cross-section, which will be our defined material 1. Now that our cross-section is defined, you will notice that it's blue here in the project navigator. This is because it doesn't have a member to it yet. To assign it to a member, we can go to the members folder, and right-clicking on members, we select new member. Within this dialog, we can assign up here the member to a line. We can either type in here line 1, or once again we can assign the line graphically. Next, within this drop-down option here, we can select the member type. For now, we are going to keep that as a beam. And below that, there is the option to rotate the cross section as well. If we click, for instance, here, we can see this rotation here in the graphic on the right side. Moving on down here, we can assign the cross section for this member, and we'll keep that for the member start and the end the same. We can also add member hinges, but we don't need that for this example. So we click OK, and if we turn off the wireframe model, you can see in the graphical area the cross section has been rendered. Now that we have all model data that we need, we can move on to the load cases and the loads we'd like to apply. Remember, before assigning any loads, we'll have to define a load case. We can do this by going to the load cases and combinations folder in the project navigator. With right click on the load cases, we choose new load case, and you can see in this dialog the program has already created our first load case. Within this tutorial, we are going to have only one load case, so we can keep that and choose all loads here. Then we can deactivate self-weight because we don't want that to be taken into account for the results later. Next, we will continue with the member load, and if we expand the loads tab in the project navigator, you will find for every load case that you have created a new folder. Since we just have one load case, we will expand this one here, and you can see here the options for different loads like nodal loads or surface loads and so on. We will choose a member load and open up the dialog for that. The load type here, we're gonna keep that as force, and for the load direction, we can keep that as the global member length in the Z direction. For this example, we are going to apply a triangular load, and for this we use a load distribution of trapezoidal. We can see up here on the right side how this load is applied on our member, starting with a load P1 and a load P2 ending. We can find these parameters down here in the section load parameters. Since we want to have a triangular load distribution, we can keep P1 as 0, and we can enter here for P2 5 kilonewtons per meter. For this example as shown, we don't want the load to be applied over the entire member length. And to do this down here, there is this option, we can turn this off, and we can set where our load will be on the member. So the start point will be point A. We can type in here 1.5, and end point B will be 3. Up here, we will then choose the member graphically, and we can click OK once again. Now the load is applied to our cantilever beam. As you can see this in the graphical area. To show the results for this load case, we'll go up to this button up here called Show Results, and then we click OK. Now you can see our results are displayed, and again our results tab has come up here where we can choose and display the deformations of this beam or the internal forces. So guys, I hope this video was helpful to show you how to model using the dialog options in RFEM. In the next video, we will go over how to model graphically using the toolbar up here. And thank you for watching. If you have any questions, you can write in the comments below or also on our website dlubal.com.